Thank you, Jacob, for the introduction, and thank you, PGO, for hosting this event. Thank you all for being here today. I'm excited to give my talk about the application of physics to financial markets. I think most of you know me. For those of you who don't, please allow me to introduce myself. I am Hank Thurston. I'm a third-year PhD student. I'm also the co-founder and co-owner of Trinary Capital. We are an SEC-registered financial advisory firm. We've been operating for just about a year now. When we started Trinary, everybody we brought onto the team brought a specialization, some sort of unique skill that would help us grow and build. What I brought to the table was my skills as a physicist. And today we'll look at how the skills that we've developed and honed over the years as physicists not only are very applicable to the financial market, but actually find a very natural home in finance. So I posed a question to the audience: who is the world's best money manager? And by money manager, I mean hedge fund manager, investor, whatever. No? No takers? All right. Well, do you recognize this gentleman? Okay, good. I see you do. Well, as you know, in our circles, this is Jim Simons. He is probably most well known for the Chern-Simons 3-form, which is a topological geometry. It was used as a topological quantum field theory and is still used as a globally gauged invariant measure in string theory. I honestly can't tell you a lot more about it than that. In financial circles, Jim Simons is more well known for founding Renaissance Technologies. Renaissance Technologies is an investment firm that operates the Medallion Fund, which is a hedge fund instituted in 1988. In the first 10 years of Medallion Fund, from 88 to 98, Medallion Fund saw returns of 2,478.6%. Okay? The next best fund in the world, George Soros's Quantum Fund, saw returns of 1,710.1%. Certainly 1,700% return in 10 years is great, but it pales in comparison to what the Medallion Fund did with almost 2,500%. Over the lifetime of Medallion Fund, it has averaged 40% return per year. This is twice what Berkshire Hathaway has done in the same time. The question's why? Clearly, Renaissance Technologies does something different and it works for them. Well, when Renaissance Technologies hires, they don't care about your finance degree, they don't care about your business major, they don't want your MBA, they hire exclusively mathematicians and physicists. The reason they do that is because of some of the problems that show up in finance, and I've got a list of those here, and these are problems or tasks that you might end up doing as a financial analyst. Things like statistical analysis, error analysis, quantifying uncertainty in predictions, finding trends in data, quantifying those trends and making predictions on them, dealing with big data. It's estimated that the stock market produces 1 terabyte of data per day per exchange. As with most problems involving big data, machine learning is becoming an ever-increasingly integral part of that. Quantifying stochastic processes, these play out as market dynamics, and just generally thinking outside of the box and bringing new perspectives and new ways of tackling problems. Now, I hope that you're looking at this list and you're thinking, hey, I know how to do some of these things, or maybe all of them. And I think it's true that physicists are really the only people who are trained, at least to some degree, in every single one of these items. Next, I want to look at some historical context of how physicists became an integral part of the financial markets. We talked about Jim Simons just a second ago. We have Isaac Newton. Now, despite being a brilliant physicist and mathematician, Isaac Newton never actually applied mathematics to the financial markets. However, he did make a very astute observation, and it's one that I hope I remember to reiterate throughout this presentation. After losing a large amount of money in the British markets of the time, Isaac Newton reportedly said, "I could calculate the the motions of the heavenly bodies, but not the madness of men. And it's important to remember that at the end of the day, at its very foundation, the market is driven by human emotion. And that's something that can never be quantified. The market's big enough, we can approach it in almost a statistical mechanics sense. But any mathematical work we do on it, we have to always remember to put in context of macroeconomics and in context of human emotion. And it's when we fail to remember that context that we get into trouble. The next name on this list, and I apologize in advance for my mispronunciation of the French names on this list, we have Louis Bachelier. He was a French mathematician in the late 1890s. I believe he published his thesis in 1899, and he was decades ahead of his work. He wasn't really appreciated at the time, and it wasn't only until the 1950s when he was really rediscovered and his work was appreciated. There was a professor in Chicago, and he and his students were preparing to publish a paper that they thought would revolutionize the way markets were analyzed and traded. He was doing some research. He was in the library looking at sources, and he came across this dusty old book. It was a copy and a translation of Bachelier's thesis. He opened it and started reading through it and found it interesting and kept going and realized that all of the math that he and his students had just worked out, that they thought was going to revolutionize the market, this had all been worked out 60 years ago by Louis Bachelier. And in fact, Louis Bachelier worked out the mathematics of the random walk 6 years before Einstein did. Now, there were two real reasons why Louis Bachelier was not appreciated at his time. One was the French class system at the time. Louis Bachelier went to kind of the second tier of universities. So he still got a good education. He was still able to get good employment, even in academia, but he didn't have the social capital that went with going to the top tier universities. Secondly, the field of mathematics was in an existential crisis at this time. In the years leading up to this, a number of long-standing theorems had been disproven, and mathematicians were shaken, wondering what was happening to the foundation of their science. So mathematicians kind of circled the wagons and looked inward, trying to get their own house in order before they applied their science to anything else. So at that time, they were extremely hesitant to accept seriously any work like Bachelier's applying pure mathematics to something like finance. To this day, within financial circles, Louis Bachelier is quite well respected, though unfortunately outside of finance he is still relatively unknown. Blaise Pascal worked out what we would consider modern statistics, and his motivation for that dealt with gambling, but the same statistical analysis can be applied to the market. He did this with the help of Fermat. MFM Osborne is a more modern physicist. He worked along some of the greats in the 1940s and 50s, and later in his life focused almost solely on analyzing financial markets. And this is certainly a non-exhaustive list. There are many, many other examples. This brings us to the so-called quant revolution. And this originated in the 1980s, brought on by the advent of digital communication and electronic trading. But it really took off in the early 2000s. You had quantitative analysts, primarily physicists and mathematicians, who were developing algorithms, looking at market data, creating new trading strategies unlike anything that was ever seen before, and it worked great. But then something happened in 2007. Now, all of these models that they've been using for a decade that were working great, lots of people were making lots of money off these models, but then all of a sudden one day they just didn't work. Assets that were predicted by these models to go up went down. Worse yet, assets that were supposed to go up when these other assets went down, well, they also went down. This initiated a market crash. The quantitative analysts were able to pivot very quickly, reassess their models, look at what was happening in the market from a data perspective, refine their models, and try to develop new strategies to pull out of that market crash. And this, coupled with an influx of large capital from large banks, was able to halt the market crash and return the market to good performance, at least for another year or so. And that brought on the housing bubble of 2008 and the subsequent market crash. And that's a fascinating topic in and of itself. But suffice it to say for now that quantitative analysts played an integral role in that, and they were also central to rebuilding the market afterwards and putting in controls that would hopefully prevent something like that from happening again. They were instrumental in rebuilding the recovery from the market that turned into the longest bull run in American history. So with a little bit of background and historical perspective out of the way, I'd like to look at a couple concrete examples of how we can apply our knowledge of physics to analyzing financial problems. Before we get into our first example, though, I want to provide a little bit of background on options just so everyone's starting at the same level. Options are a class of derivative that give an investor the right, but not the obligation, to buy or sell a stock at a predetermined price and date. There are two styles of options. There are American options, which may be exercised at any time from purchase through the expiration date. And when we say exercise or execute in regards to options, it simply means that the investor is choosing to take their right to buy or sell at the predetermined price. In contrast to American options, we have European options, which may be exercised only on the expiration date. There are two types of options. There's a call option, which is the right to buy a stock at a predetermined price. This can be a strategic move if you expect the price of a stock to go up. And counterpointing the call, you have the put option, which is the right to sell a stock at a predetermined price. And this can be a strategic move if you expect the share of stock to go down. As I said, options have an expiration date, and after the expiration date, the option is null and void and considered worthless. Options have a strike price, which in this presentation we'll denote by the variable K, and strike price is simply the predetermined price at which the investor has a right to buy or sell. The first example I want to look at is probably the preeminent example of an equation of mathematical finance, and that is the Black-Scholes equation. This was published in 1973 in the Journal of Political Economy by Fisher Black, Myron Scholes, and based largely on the work of Robert Merton. They showed that it's mathematically possible to eliminate all risk in a portfolio, and this is a technique that we now refer to as continuously revised delta hedging. But like all of our physical models, we rely on certain assumptions, and the assumptions involved in the Black-Scholes model is the assumption of a frictionless market. A frictionless market is a market where there are no transaction fees, there's no arbitrage, and there is no limit on short selling. We'll look at a little bit of nomenclature. We have stock price, which we'll denote as capital S. We have T, which will denote time. We have option price V, and V is a function of S and T. We have portfolio value P, and we can think of this as a portfolio of one option and delta shares of stock. The change in portfolio value dP is then dV plus delta ds. Now it's easy to look at delta and think of that simply as the number of shares of stock in the portfolio, but I would encourage you to think of delta more as a scaling factor or a weighting factor that we use to multiply by the change in stock price to reflect the value of the portfolio. And you'll see why that perspective of delta makes sense in a couple slides. Another bit of tangential knowledge necessary to continue the derivation of Black-Scholes is Ito's lemma. Ito's lemma is used to find a differential of a time-dependent function of a stochastic process. Roughly speaking, this is the stochastic calculus analog to the chain rule of ordinary differential calculus. So given some Brownian motion B of t and some drift diffusion process W of t, which satisfies equation 1 on screen, then if f of omega t is twice continuously differentiable on R2 and R, then f as a function of Wt and t is also a drift diffusion process whose differential is given by equation 2. And we'll use both equation 1 and 2 to derive Black-Scholes. So using equation 1 directly, we'll define ds as mu s dt plus sigma s d omega. Then with Ito's lemma, which is equation 2, we can write dv as partial v partial t plus mu s partial v partial s plus 1/2 sigma squared s squared partial squared v partial s all times dt plus sigma s dv ds times d omega. Now we have an expression for dv and ds, so going back to our expression for portfolio value, dp equals dv plus delta ds, we plug in these two expressions and we get the equation that you see at the bottom of your screen there. Now we need to remember why we're doing this. We want to create a portfolio that is perfectly hedged. We want to create a riskless portfolio, which means we want a non-stochastic portfolio. We need to remove randomness from it. So the first way to do this, we're going to define delta as the negative partial derivative of v with respect to s. And this is why I wanted you to think of delta as more of a weighting factor rather than the number of shares of stock. And maybe this makes you a little bit uncomfortable, but we know that v is a function of t and s, so it's fair that we can write this derivative. And we know that as the stock price changes, the value of the option will have to change with some correlation to that. And then there must be a way that we can express delta such that we multiply delta by the differential stock price to reflect the overall value of the portfolio along with the differential of options value. And the way we do that is through this negative partial derivative. We'll also write another expression for dp. In this case, dp is equal to r times p times dt, where r is what we refer to as the risk-free interest rate. And the risk-free interest rate is the interest rate at which, if we put portfolio value p into the bank and we earned interest on it, it would be the interest rate at which we would have the same amount of money from the bank as we would from our gains in the market. We now have two expressions for dp, so we can equate these expressions, and then using our long form expression for dv plus delta ds, we can put all of this together and we get the equation you see on screen there. And this is the Black-Scholes equation. Partial v partial t plus 1/2 sigma squared s squared, partial squared v partial s squared plus rs partial v partial s minus rv equals 0. Where sigma squared is a risk factor, essentially the variance in stock price. Now, personally, I find this quite elegant. With that said, I would not want to see this on an exam. So we have to ask ourselves, is there a way that we can make this more tractable? And the first thing we notice about Black-Scholes is we know the value of the option as a function of s and t at the time of expiry. So we have a system where we know the terminal condition but not the initial condition. Therefore, the first change of variable I want to make is I want to define variable tau is equal to big T minus little t, where big T is our total time. This, in essence, reverses the time domain. Next, I'll define x as the natural log of share price s divided by strike price k. And then we'll write a function a function z as a function of x and tau. And z is simply our function v with the new variables. So z of x and tau is equal to v of k times e to the x and t minus little t, or t minus tau, excuse me. We can then rewrite Black-Scholes using our new variables, and it takes the form that you see on screen there. And we now have a partial differential equation with an initial condition given by z of x at time t equals 0 is equal to v of k e to the x and big T. We're almost there. Now I want to define one more function, and that's u as a function of x and tau, and u is equal to z times e to the alpha x plus beta tau. We can then plug u in and rewrite the Black-Scholes equation in terms of u, and we end up with the expression you see on screen where a and b are whatever combination of constants are necessary to make this work. Next, we want to make a and b both equal to 0. And again, this might make you a little bit uncomfortable. But the reason we're able to do this is because we defined u to be pretty much whatever we want it to be, and we still have two variables we haven't even touched, namely alpha and beta. So we can find an alpha and a beta such that a and b are 0, and this will still work. And when we do that, we find that alpha is equal to r over sigma squared minus 1/2, and beta is equal to r over 2 plus sigma squared over 8 plus r squared over 2 sigma squared. Now that a and b are both 0, we have this equation. And this is something we all recognize. If I run into this on an exam, I'm happy. The diffusion equation, fixed second law, the heat equation, whatever you want to call it, we know what it is, and more importantly, we know how to solve it. And equally importantly, we know how to interpret it. We need boundary conditions for our systems, and the boundary condition depends on whether it's a put or a call option. In the case of a put option, as s approaches infinity, v approaches 0, and for a call option, as stock price s approaches infinity, options price v approaches s. Now this can be solved analytically with these boundary conditions for the case of European options. But what about American options? We've already said that American options are more complicated because the option can be exercised at any point from purchase to expiration. So American options have to be solved numerically. And the way this is normally done in practice is through a binomial pricing model. And there's an example of that on screen here. So what we have is we start with the current stock price, and we can calculate the option value from that. Then we look at a certain probability that the stock price will either go up by a certain amount or down by a certain amount. And we can calculate the corresponding option value there, and we keep branching out in a binomial tree. Because this is an American option that can be exercised at any point, for every one of these nodes, we have to check whether it is more valuable to hold the option or to exercise the option. And as I said, this is used regularly in practice because it's easy to understand, it's simple to implement, but there are problems with it. This takes something that is inherently continuous, the value of the option, and it forces it onto a very coarsely discretized discrete domain. And when you do that, you lose information. So I personally believe that you're better off solving Black-Scholes numerically. However, there's some problems doing that. Typically, we use a finite difference method, but because the Black-Scholes or the diffusion equation is a stiff equation, it requires an implicit or an implicit-explicit method for numerical stability and convergence of the algorithm. When we do this, again, because of the American option, we have to check at every time step delta t whether it's more valuable to hold the option or exercise the option. The first thing we do in order to determine this is we define the payoff function f. And this is the payoff of the option should it be executed. And this again depends on whether it's a put option or a call option, but f is the max value of either the difference between k and s or 0. And whether we take k minus s or s minus k depends on whether it's a put or a call. Once we've calculated f, we can then compare and determine whether it's more valuable to hold or exercise the option. To do this, we take the minimum value of v at time step tau. And remember that this is a time step process, so we're doing this analysis at time step v at tau plus 1. So we look at v at time step tau minus the Black-Scholes equation, or v minus f. We take the minimum value of those. One of those has to be greater than 0. It makes sense that the value of the option can never be less than its payoff, which is why this has to be greater than 0, because if it were less than its payoff, you'd have an arbitrage condition in the market that would be unstable. So that pretty much concludes our derivation of Black-Scholes. If you are interested in Black-Scholes, its derivation, its application, or numerical methods to solve partial differential equations, there's an excellent paper. It's a master's thesis out of Waterloo University that walks through the derivation of Black-Scholes, the derivation of the American pricing scheme, as well as several numerical methods to analyze it. It's an excellent resource. It's listed in my references at the end of the presentation, and I'll point it out to you then. The second example I want to look at is optimizing the Markowitz mean variance portfolio theory. Again, we'll start with some nomenclature. We'll define return as big R equal to the money paid out divided by money invested. We then have the rate of return little r, which is equal to the money paid out minus the money invested divided by money invested. And these two are related as little r equals big R minus 1. We can calculate both big R and little r for individual assets or a portfolio as a whole. Now, to keep these separate, when we're looking at the individual asset, these will be denoted by a subscript I, and when we're looking at the portfolio as a whole, this will be denoted by a subscript P. We assume that we have a portfolio made up of n number of assets, and each asset has a portion of the total amount of money in the portfolio assigned to it. And we will call this weight Wi. All of the weights Wi have to sum to 1. We can define return on the portfolio as equal to the sum of 1 through n of capital Ri times Wi, and the rate of return of the portfolio, lowercase r, as equal to the sum of 1 to n of little ri times Wi. We want to maximize the rate of return for the portfolio. So what I'm going to do is create a vector m, and this vector will hold the expected values of each ri. We'll then define a variable mu, and this will be equal to the expected rate of return of the portfolio, which we can express as the sum of I through n of Wi times mi. We need to keep in mind what our goal is, and our goal is to find the optimal weighting factors Wi. And right here I want to take a little bit of an aside. This is a technique that is used regularly in practice for actual money management. And as you've seen, the idea is that we take this portfolio that has all our assets in it, and then we want to find the optimal amount of money to apply to each one. However, again, there's a problem with this. And so at Trinary, we've chosen to tackle this problem a little bit differently. Rather than trying to optimize all of the WIs, because you can optimize all day, you can optimize till the cows come home. But if your portfolio consists of sub-optimized assets, it doesn't matter how well you allocate money between them, you'll see suboptimal performance. So when we solve this problem, rather than solving for the WIs, we solve for the RIs, or more specifically, the assets behind the RIs. Another way to think of it is, instead of the solution space to our problem being the numbers between 0 and 1, when we solve it, the solution space is every financial asset in the world, or at least a subset of those that we are interested in looking at. But going back to mean variance theory as it is typically done in practice, our goal is to find the optimal weighting factors Wi. We define the variance of the rate of return of the portfolio exactly as we would expect, with the expected value of r squared minus the square of the expected value of r. We can write this as the double sum over I and j of Wi times Wj times a quantity of expected value of Ri times Rj minus the expected value of Ri times the expected value of j. We can write this in matrix notation and then express it as the double sum over I and j of wi times eij times wj. This introduces the covariance matrix E, where each element of the matrix eij is equal to the expected value of the product of r minus expected value ri times rj minus expected value rj. The covariance matrix E is symmetric and positive semi-definite. This means it is Hermitian and all of the eigenvalues are non-negative. All of the market information is contained in matrix E. We want to minimize some function f, and our function f is the double sum over I and j of wi times eij times wj. But this is subject to a couple constraints. Our goal is to minimize risk or minimize variance for a given rate of return. So to do that, we'll express the first constraint as mu minus the sum of mi wi equals 0. The second constraint is that all of the wi's have to sum to 1. To solve this problem, we get to use one of my favorite things to come out of physics. Actually, two of my favorite things to come out of physics: the Lagrangian and the Lagrange multiplier. So I'm using Dirac notation here for simplicity, but we can write the Lagrangian as 1/2 WEW plus lambda 1 times mu minus the inner product of W and M plus lambda 2 times the inner product of W and V, where V is the vector of all ones. From this, we get the typical Lagrangian equations of motion, and we can express this as a linear system of a 2x2 matrix as shown on screen there. Now we can simplify this matrix a little bit just notationally. We can write it as a 2x2 block matrix with elements j, k, and l. Again, just for simplicity of notation, let's define that matrix as D. So our linear system becomes D times our lambda vector is equal to the vector of mu and 1. This system is pretty easy to solve directly, and it leads us to the solution that our vector W is equal to mu L minus K over determinant of D times the inverse of E times M plus J minus mu K over determinant of D times the inverse of E times V. And this vector W contains all of the optimized weights for the portfolio. There are some other considerations of mean variance theory. One is that the covariance matrix typically requires some additional work. As with most things that we do with linear algebra, it's convenient to write this in a basis where it's diagonal. To do that, we can think about singular value decomposition. Through SVD, we can express variance in terms of the eigenvalues of E, and that makes the problem nice and simple. There's also a noise to signal concern. Now, in a perfect market, all of the RIs are not correlated. So you might think that in a perfect market, the covariance matrix should be the identity matrix. However, even in a perfect market, the only way that the covariance matrix becomes the identity matrix is as the ratio of length of time series over number of assets approaches infinity. And by that I mean we have some sort of time series data. For instance, we have end of day prices for the last 10 years. So that's roughly a length of 2,500 days. And say we have 5 assets in our portfolio. So that gives 2,500 over 5 is 500, which is a long ways from infinity. Really what I'm saying here is that E is noisy. So we either need to find a way to denoise E, or we need to boost the signal in E. And there are a couple different methods we can apply to do this. Different methods are more applicable in certain situations. But we have random matrix theory, which can place upper and lower bounds on the allowable eigenvalues of E. We have LCBP, which replaces noisy eigenvalues with a mean eigenvalue. We have PG+, which replaces noisy eigenvalues with 0. And then we have KR, and KR is interesting. So KR adjusts noisy eigenvalues a little bit such that the system becomes more stable. And by more stable, I mean that the corresponding eigenvector becomes less sensitive to small perturbations in the corresponding eigenvalue. But this is really an open-ended problem, and there's lots of work that could yet be done on it. So in conclusion, I hope we've seen that there are many elements of market dynamics that share the same form as physical systems that we're familiar with. And as physicists, we are uniquely equipped to investigate, analyze, model these systems, and develop trading strategies based on that. The skills that we've developed and honed over the years in physics give us new insight to new ideas and alternative approaches to understanding the mechanisms behind financial markets. We have the mathematical skills to work these problems out. We have the problem solving and critical thinking skills. We have the understanding of the physical world. We're able to link the abstract maths with the physical. We have the ability to learn and to teach ourselves, and especially on the experimental side, we have the ability to adapt and to fix things when they break and pivot and get things working. And for these reasons, physics and our skills are very much at home in the financial world. If this kind of thing is of interest to you, here are certainly a non-exhaustive list of other physics type models that are currently in use in the financial world, as well as a couple books that I think are good reads on the topic. And I can put the slide back up later if you would like. These are the references I've used throughout this presentation. I mentioned the third reference, that is the Ming Ma paper. It's a master's thesis out of Waterloo University. And if you're interested in Black-Scholes and partial differential equations and numerical methods, that paper is probably the best source in the world for solving that particular problem. So that pretty much concludes everything I want to talk about today. At this point, I'll be happy to take any questions.